Hi everyone. Today we continue with the second part of the vector algebra, which is in the week 4 topic, vector algebra part 2. And in this week topic, actually you need to cover is quite lengthy. I'm not so sure whether we can cover everything by week 4. If not, I will continue in week 3. So the topic is that we will cover under vector algebra 2 is the dot product, application of the dot product in geometry, and then equation of line in 2D and 3D space. Then only we look into cross product, application of cross product in geometry, and lastly will be scalar triple product. Okay, after I continue week 4, then only I go back to the week 3 notes where we do curl, divergence, and also gradient. Alright, before we move on even further, let's look at the product or multiplication of two vectors. Okay, if you multiply two vectors, there are two ways of doing it. One is called the dot product, another one is called the cross product. The difference between these two product is the dot product will give you a scalar value, while the cross product will give you a vector value. So what does it mean by this? The dot product will give you a magnitude only. So you will always get the answer in terms of the numbers. It only has a magnitude, doesn't have the direction. However, sorry for that. However, the cross product will produce a vector, which is it has the magnitude and it has the length. Okay, so this is called a vector product, whereas the dot product we will call it as scalar product. So let's look at dot product first. Okay, so the dot product, the way we have to say it is a, not a multiplied by b. Because in vector it has two types of product, multiplication. One is dot, one is vector. So the way we have to we have to say it is a dot b. So a cross b is actually cross product. But dot product we have to say it as a dot b. So the a dot b in the vector is given as this. Magnitude a dot b is equivalent to magnitude of vector A multiplied with magnitude of vector B cos theta, where theta is in the range of 0 to 180 degrees. 0 to pi, 180 degrees. Alright, and this theta is actually the angle between vector A and vector B, and is measured when the vector have their initial point coinciding. So meaning like this, we have the vector A and we have the vector B. So the angle of theta is in between vector A and vector B, and the initial point are coinciding with each other. Okay, how we get into this? How the A dot B become A, magnitude of A multiplied with magnitude of B cos theta. Okay, let's look at law of cosine. Law of cosine said that a minus b squared is equivalent to a squared plus b squared minus 2ab cos theta. So if you expand a minus b squared, you will get something like this. You multiply a minus b with a minus b, and when you expand it, you will get this one. You multiply it together, you will get a squared minus 2ab. First you get negative AB, then you get negative AB plus B squared. Alright, so the 2AB here, the 2AB here. So here, I put it down here. It looks this one. Okay. And A squared minus 2AB plus B squared is also equivalent to this one. Because law of cosine said this. Okay, so this one, after I expand, I put it here, and this one is equivalent to the law of cosine, and we can rearrange actually. And when we rearrange, we will see that the A and A can be minus together, and it will be removed, and B squared also will be removed, and here can bring it up here, negative 2AB plus 2AB, you will get 0, and it will leave with sorry, no 2AB is bring it here. Let me write. This one and this one cross it, and it will remove, and you will live with negative 2ab equivalent to negative 2ab cos theta. Okay, so here negative 2 can be removed and leave it with a dot b equivalent to a b cos theta. Okay, and the property of the dot product vector is if you multiply a dot b is equivalent to b dot a, because it only gives you scalar, and the multiplication of the vector is the same, like the vector multiply with another vector b plus c. So you just a multiply with b, a multiply with c, and so on. Okay, and the scalar, if you multiply scalar with the dot product, you will get something like this. And always remember that when you do dot product, you always get a scalar. Okay, alright, let's go into the orthogonal vector. When we say orthogonal, we are talking about 90 degrees or perpendicular vector, perpendicular or normal vector. So you have, let's say this is vector A, and then this is vector B. So if these two vectors are perpendicular to each other, they are 90 degrees. And cos, if you take, okay, just now it says that, hold on, let me erase this. Just now it says that A dot B is equivalent to magnitude of A, magnitude of B cos theta. However, here cos 90 degrees is, if you click calculator, it is equivalent to 0. So cos theta is 90, and theta is cos theta will be 0. Okay, so the dot product will be 0. So if there are two vectors that are perpendicular to each other, the dot product will be 0. A dot B can be 0. A dot B can be 0 if either one of that vector, A or B, is 0 vector, and or they are orthogonal vector, meaning that A and B are 90 degrees with each other. Because if you click calculator, cos 90 degrees, you will get 0. Okay, so having said that, we do know that this is, if I draw the x, y, and z vector, this is I vector, this is j vector, and this is k vector. So they are always 90 degrees with each other. I and k 90 degrees, I and j is 90 degrees with each other, j and k is 90 degrees with each other. Therefore, I dot j will always be 0 because they are 90 degrees, cos 90. J dot k is equivalent to 0, and k dot I is equivalent to 0. Okay, and we have a parallel. Okay, that one is if you have the vector that is perpendicular to each other. Perpendicular to each other. How about we have the vector that are parallel to each other? This one is perpendicular, this one now is parallel. Parallel means that, okay, you have this vector A, and then another vector is like this, same direction. It may be different length, but then both of them have the same direction. Alright, so the dot product, it would be A dot B, A B cos theta. However, now the theta angle is 0. Okay, so if you click calculator, cos 0, you will get equivalent to 1. Okay, so the dot product of two similar vector will be A dot A will be A squared, and the dot product of a unit vector will be equivalent to 1. So you will get A dot B will be magnitude of A multiplied with magnitude of B, because cos theta now become equivalent to 1. So having said that, if you I dot I, any vector that is parallel with I dot I, you always will get 1. J dot J, you always get 1, and K dot K is equivalent to 1, because the magnitude of I dot I will be like I magnitude multiply with another I magnitude cos 0. So this one is equivalent to 1, this one is multiplication 1, course 0 will be 1. So that's why you always get 1. So I dot I, j dot j, and k dot k will always equivalent to 1. However, if they are dot product between two axes, because they are 90 degrees, they always will get 0. Okay, so hold on. Okay, I continue a bit. How we get from a dot b, how we get it becomes scalar like this. So let's break it down here. So the a vector is ai, a1i, a2j, and a3k dot with vector b, b1i, b2j, and b3k. And then we multiply like normal. So we get first a1 b1, a1 b1, and then vector I dot I, and then and then we can get a2j b1, j dot I, a3 b1 k dot I, a2 plus a2 b1 j dot I, a2 b2 j dot j, and then a2 b3 j dot k plus a3 b1 k dot I. So you just multiply like normal. You just multiply like normal. You will get the expansion like this. And we know that if j dot I, k dot I, if a dot product, you will get 0 as what we encounter here. And due to that, so this one can be just scrap off because it will be 0, and you left with a1 b1 I dot I, and then a2 b2 j dot j, and then a3 b3 k dot k. And we know that I dot I equivalent to 1. This one, j to j, j dot j is equivalent to 1, and k dot k equivalent to 1. So at the end, you will get it's just a1 b1 plus a2 b2 and a3 b3. So therefore, dot product a dot b will get only a scalar value. Okay. Alright, please do this exercise, and we will discuss that in the class later on. You have to do it, and then we discuss it in the class later. Alright, the question is continuing. Part 1, part 2, and part 3. So you do that first, and then we discuss in the class. Alright, now I go into the projection of the vector. So let a and b be a non-zero vector, and let a prime here is a unit vector in the direction of A. So the projection of B into A. Projection means like this. If this is the line, and I put, let's say I take the torchlight. I put the torchlight. This line will be projected into this vector. That's what it meant. Okay. So the projection of B onto A, this is vector A, is defined by B dot vector unit A. Okay, so vector unit A, we know vector unit A is given as vector A divided by magnitude of A. Okay, so the component that we say, the component of B in the direction of A is defined by B dot A in the direction of A. Okay, so geometric interpretation, the angle between vector B and I here, the theta here is actually B dot I cos theta, and the magnitude of I is 1, so leave it with B cos theta. Okay, so this is equivalent to ON, the length of orthogonal projection B on the straight line in the direction of I. Okay, alright, so the projection can be in terms of the negative or positive, that positive or negative like this, depending on the sign of the vector. If it's negative, meaning that the direction is vice versa lah. Okay. Alright. And if A is a given vector, then any vector B can be expressed in terms of, can be expressed as a sum of the vector parallel to A and also vector parallel to B. So imagine like this. If we want to find the vector OM, the vector OM is actually ON plus NM. Okay, so the vector ON is actually B1 plus B2. Okay, and previously we know that the ON here is actually projection of vector B onto vector I. Okay, so projection of vector B onto I in the direction of I, direction of vector A. Okay, so we can express it as in like this, B dot A unit vector in the direction of unit vector. If we expand, it will look something like this. Okay, so this is what it meant by B dot A multiply with A, and A, magnitude of A multiply with magnitude of A is squared below. Okay, or you can express it in term of this way, also okay. And OM is B. Okay, so if we want to find the NM B2 is OM, and M is here. If you want to find NM, and M is OM minus ON. OM just now is B, minus ON this one. Okay, B dot A dot A dot A in the direction of A. Okay, so this is NM. Okay, alright. So we can rearrange, if we rearrange once again, we can get, this is NM, NM, typo. Okay, if we rearrange once again, OM is B, ON is given as this, we replace it, and NM is actually given as this. So this means that this is the parallel component, and then this is the perpendicular component. Okay, ON is the parallel component, and then this one is the perpendicular component. Alright, so there's another exercise here that you should try, and then we will discuss it in the class later on. Okay, alright, 4.1.2 I will do another video. Alright, now we look into 4.1.2, which is the application of dot product in geometry. Okay, so we can use dot product to find line equation and extend it to the plane equation. It's just that this line equation is 2-dimensional and this one is 3-dimensional. Okay, besides we will use it to find distance between point to line, and then point to plane, parallel line, and parallel plane. Again, it depends on the whether it's 2-dimensional or 3-dimensional. If we are dealing with 2-dimensional, we just dealing with the point and line. But if we are dealing with 3-dimensional, we are dealing with point and plane. Okay, alright. Furthermore, we can also use it to find the angle between intersecting line and intersecting plane. Okay, so now first we look at the equation of line and plane. Line is 2D, plane is 3D, perpendicular to the given vector. Okay, alright. Let L is this line, this is L, passing through a point P0, which is the coordinate is x0, y0, and it is perpendicular to the normal vector AI BJ. This is the normal vector. This is the normal vector. And let P is any point on the line L, and denoted as coordinate x and y. It can be any line between any point between the line. So the vector P0 to P along the line L and perpendicular to the vector N is given as this. We know that if the vector is perpendicular to another vector, their dot product will be 0, right? We covered it just now. Okay, so if we know that P0 P dot N, P0 to P, the vector is this one, dot with N, and it is perpendicular, we know that it's equivalent to 0. So in order for us to find the P0 P is the location of the coordinate of OP minus OP0 dot N, or we can get P minus P0 dot N. So P minus P0, we know that P is vector X, Y, and P naught is vector X naught I and Y naught J, right? So in order for us to find the P naught P is P minus P naught, X minus X naught, and then Y minus Y naught, and dot product with AI B J. So in return you will get AX minus X naught plus BY minus BY naught. So negative AX naught and negative BY naught, bring it to the other side. This will be like this. Okay, so in return you will get that AX plus BY equivalent to C, where this part is actually a scalar, because we know the location and coordinate of X naught and Y naught. A and B is scalar. So this is what we call the Cartesian equation of line. Note that the component of n are the coefficient of line equation. From the Cartesian equation, we can know that information of the vector normal line n. Alright, so these are the situation when we have a 2D and the Cartesian, 2D and 3D in Cartesian form. So we can find the Cartesian equation of line as given in the example just now, and also we can find a point to line, the distance, the shortest distance between this point to this line, and also we can find the distance between two parallel line, and we can find the angle between two intersecting line. Whereas where we have the 3D plane, we can find the Cartesian equation of plane passing through a given point and normal to a given vector. Just now what we did is line and then there's a normal vector. Now it's a plane because it's 3D. And we can also find the distance between point to plane and two parallel plane and also two intersecting plane. So let's look at the first one. Just now we look at the equation of line. Now let's look at the equation of plane. Let S be the plane passing through a point P naught, which is X naught, Y naught, and Z naught, and the normal vector is AI plus BJ and CK. So let P be the point in that plane S, meaning that it's 3D now, and the vector P naught P in the plane is given as this, and this is perpendicular to the vector N. Okay, and we can do the product, and we know that if we do the product of that plane with the normal vector, which is the normal vector is perpendicular to that plane, you will get it equivalent to 0. Okay, and you can solve it, the dot product, you can solve it, and when you solve it, you will get that the equation is given as this, where the D part is actually AX naught plus BY naught plus CZ naught, that is scalar. Okay, and in two-dimensional vector, in two-dimensional, the orthogonal vector into this space, you will get the equation of line. However, if the orthogonal vector in 3D space, you will get the equation of plane. So your equation now got X, Y, and Z component. X, Y, and Z component. Okay, so you can try this exercise, and we discussed it in the class. Alright, now I go to the point to line distance. Alright. And then this one, and also the distance between point to plane. Alright, let's look at this line first. We have this line with the Cartesian equation of X plus BY equivalent to C, and let P be any point in the line L. Find the equation of line where the vector N is equivalent to AB. AI plus BJ is perpendicular to L. So previously, we learned that the projection of vector B onto A is defined as this. So we can use the same concept to find the distance of point Q here to the line L. We can use the projection of the vector concept. We project this point to this line. So given by that is vector PQ. When projection of that vector onto the line, we dot product with its unit vector. Okay, so it's given as this. Okay, same goes with the situation. Now just that the different, not finding the distance between point and line. Now you're finding the distance and on the plane. So now you project the point PQ onto the what do you call, plane S here. Okay, so now the vector PQ to the plane plane S is dot product with the normal vector here, and you will see that the difference between the formula is the same, but then again here you get the K component, because it has X, Y and Z component. This one is just X and Y. Okay. Alright, please do this exercise. We can discuss it in class. And you see that this is line X and Y, and here this is plane because you get X, Y and Z. Okay, and if we need to find the distance of two parallel line, what you need to do is the projection method is used to find the distance between two parallel line L1 and L2. Let's say this is L1, this is L2. Let us choose one point from L1, and Q is any point in line 2. So the two parallel line is actually the perpendicular vector N1 and N2 for line L1 and L2. So this is the perpendicular direction of line 1. This is the perpendicular direction of line 2. And the size is actually the same as, because it's parallel, so the size is the same. So the vector also the same, it's just that different direction. Okay, and the distance between parallel line L1 and L2 is given as the same formula as this, where vector PQ dot with the any of this vector, any of this normal vector. You can pick either N1 or N2, because they will give a same answer, because the normal line will be the same. And same goes with the plane. Now instead of you have two line parallel to each other, now you have a plane parallel to each other. So the shortest shortest distance is actually PQ dot vector unit normal, N dot N, as shown in here. Okay, here is two line, right? And please do this exercise, we discussed in the class. And if you want to find the angle between two intersecting line, we covered it previously that between vector A and B, if you do dot product, the angle between that A and B is called theta. So now we want to find the theta. So if we have two intersecting line, we can find the normal of each line, and the length of that normal, both lines, N1 and N2, you can do cos inverse N1 dot N2, you will get a scalar here, and below here also you get scalar, because it's magnitude. Okay, and the angle between two plane also the same. It's just that the difference is the normal line N1 and N2 now is the normal line for the plane instead of for the what do you call, for the line. Okay, please do this exercise. I will discuss it later. Okay, and in the 4.13 I will do in the next video. Alright, now we look into the 4.1.3, which is the application of dot product in the geometry. And why the vector is very important is actually we can use the vector to form the equation of line, whether it is in 2D space or in the 3D space. Okay, so if we have the situation where we are dealing with 2D, meaning that it's just X and Y, and also 3D space, we can find the equation of line passing through a given point and a parallel to a given point in 2D and 3D, and also we can determine whether that line is intersect in the three-dimensional space, and if it's intersect, we can find the point of intersection here. So let's look at the first part first, where we will understand what does it mean by the equation of line in the 2D space and 3D space. So imagine that we have L is a straight line. This one, the blue color here is the straight line, and passing through point A, and at the same time this line is parallel to another vector, which is vector v here. So the a to r here, the vector a to r here, a is the point a, r is a point r, and will be equivalent or parallel in vector v. And a to r is a vector where a is, let's say, one point in the line, and r can be any point on the line. So vector AR, meaning that the coordinate coordinate R minus the coordinate A, and you get the vector AR. And this vector AR is parallel with vector V. What does it mean by that? So let's say OA is called vector A, and OR is vector R. It be the position vector of vector A and R. I hope you still remember what does it mean by position vector. Position vector meaning that you find the vector of that point, and that vector starting from coordinate 0, 0 to vector A. So this is OA. So position vector of A and R denoted as vector A and R, and this AR actually in parallel with vector V. So meaning when you say parallel with vector V, it has the same direction. But then the magnitude will be different depending on the parameter of t here. It can be any real integer value. And hold on. Sorry, I continue. If let's say one vector is in parallel with other vector, so meaning that it can be expressed in terms of it is equivalent to that vector multiply with one scalar here. So I can express AR equivalent to TV, where T is actually a scalar. So what does it mean by this? It means that as the T value changes, we have all the point in L. And bear in mind, this scenario can only be expressed if this vector, AR vector and V vector are parallel to each other. So in this case, the AR vector is parallel with vector V. So if we follow the head to tail method, in order for us to find what's the resultant here, we want to find OR. What we need to do, we need to add the resultant, which is the OA plus with the vector AR. Plus with the vector AR. And OA here, I represent it as AR, and OR here is R. Alright, so the AR here, but AR here can be expressed in terms of T vector V. It is a scalar multiplied with vector V. So as long as T changes, the variable of or the vector of AR will be changes. So we get R is equivalent to A plus TB. So this is called a vector equation of line. And the V is called the direction of vector of the line L. Alright, so from that, this one, this is what we call the parametric equation. Parametric equation of line in 2D and 3D space. So let's say we have point in the 3D space. 3D space, now we have the vector R, which is now you have xi, yj, and zk. Sorry, let me erase this one. So now this is vector in 3D space. 3D space, where x represent the vector in I direction, y represent vector in j direction, and k represent vector in z direction. Okay, so the position vector of a point passing through a line L, which is L now, A now. A is, if you remember, A is here, vector A. A can be denoted in the 3D space equivalent to A1 plus A2J plus A3K. And the direction is parallel to point V. Point V is V1I, V2J, and V3K. Okay, so this is a point at time t, and this is actually the initial, what we call the initial point. and then here is called the direction vector. Okay, this is called the direction vector. Okay, so by comparing the I and J component, if I break it down, meaning that I break it down in X direction, in Y direction, and in Z direction, I will get like this, where R is equivalent to X, Y, Z, where X is actually A1 plus TV, A1 plus TV, Y equivalent to A2 plus TV2, and A3 equivalent to A3 plus TV3. So this is what we call, these three equations here are what we call the parametric equations of line L. Okay, and if I rearrange the equation of X, Y, and Z here, I make it representing in terms of T. For the first one, X is equivalent to A1 plus TV1. T here will be X minus A1 divided by V1. So I bring it down to here. And for the second equation, T here, T will be Y minus A2 divided by V2. And T here will be Z minus A3 divided by V3. Okay, so this is T, T, and T. So we can make it equivalent. T is equivalent to X minus A1 over V, equivalent to Y minus A2 over V2, equivalent to Z minus A3 over V3. So this is format for Cartesian equation or symmetric form. This one just now is the parametric form, and this one is the geometric form of the line. Alright, so now let's look at the intersection between line and a plane. If we know the information of a plane and the line equation are given either in the format of vector equation like this, and this is vector equation, and or parametric equation, which is like this format, or Cartesian equation like this, so we can know more detail about the information of the plane. For example, like this, the line intersect at a specific plane. This specific plane, this is the plane. The plane must be in 3D. However, there's no, this one, the boundary here. However, for this case, there's no parameter in terms of the Z. Z will be equivalent to 0. So it's only X and Y plane. It's only in Y and Z plane. This is Y, this one is X. Hold on, this is X, this is Y, and this is Z. So the plane here only exists at Y and Z plane. Y and Z, and X is 0. Let's say the parametric equation have been derived from a given information of point A passing through the line, and the vector direction of L, V, are given as well. We can use parametric equation to solve for T, Y, and Z. We can get information from that because we can make it equivalent to each other. We have the X equivalent to A1 plus TV1, and Y equivalent to A2 TV2, and Z equivalent to A3 TV3 here. Please correct it in your notes. And then the point of intersection in YZ plane can be obtained. So the plane equation is normally in this format, where you have AX plus BY plus CZ. So you have three components, X, Y, and Z, equivalent to one number here, one scalar here. The step is similar as above, given that the A, B, C, and K can be substituted into parametric equation and we can solve it for T. Alright, and from here, we know that using the parametric equation or Cartesian format, we can find the intersection between two lines. We can make, if let's say we have two lines, and they are intersect with each other. The point where they intersect is called the vector R1 equivalent to vector R2 because they are intersecting with each other. So they are colliding at the same point. So due to that, we can make R1 equivalent to R2, and from that, let's say this is the equation for the first line, this is equation for the second line, we can find what's the value of T here. And it means that the three equations A, B, and C must satisfy if the two line L1 and L2, this one typo, are intersecting with each other. In other words, if the parameter T is obtained from equation 1 and the parameter S can be obtained from equation B and will not satisfy equation T if there is no point of intersection. As long as they are intersecting with each other, we can make it equal, and then we can solve the T and the S here. However, if they are not intersecting with each other, we cannot make the first x1 and y1, x1 and x2 equivalent to each other because they are not intersecting. Alright, and next we go on the linear combination. A linear combination of two or more vector is a vector obtained by adding two or more vector with different direction which are multiplied by scalar value. So let's say formula, we want to find the V1. So the scalar of alpha 1 A1 plus A2 alpha 2 plus A3 alpha 3, whatever the vector that you want to add in, as long as it starts with the initial condition and then the vector can be added up together until it reach the terminal point. Okay, and the vector is said to be linearly dependent if linearly dependent if the determinant of the matrix is 0, or not equivalent to 0. It goes to infinity here. But they are linearly independent if they are not equivalent to 0. Vector are linearly dependent if none of them can be expressed as combination of ideas. Meaning, if we multiply the scalar, one scalar number to that vector, if we add them together, we cannot get it 0. So the vector are linearly dependent if the determinant of matrix is non-zero, meaning that the rank of the matrix is equal to the full rank. So we can, never mind, we have a look at the example later on, okay?